Yeah, you can start.
Okay. Good morning, everybody. So we start with our lecture today. It is a continuation of what we have started yesterday. And we introduce the phase change phenomena and mixture formation. For that, we have derived the two additional questions for the rate of change of the size of droplets and for the temperature of the droplets. And we come out with these two equations in which we have the evaporation rate and we have here the quantity of heat we transfer to the droplets in time. And we got this expression for the evaporation rate in which we have the effective Sherwood number, and we have here the Spalding mass transfer number. We obtain the same with this expression for that. And in this expression, so we had also the effective Nusselt's number. And for that, this quantity could be determined in this following way, as we have seen yesterday. And to determine this, we need this value, the mass fraction at the interface, because this one is derived by the Carrier phase calculation. And this can be determined here by using the equilibrium model, for example, and the non-equilibrium model. For the equilibrium model, so we have this expression for this F2 and this one for non-equilibrium model. And the expression for the other, for the heat transfer is obtained as we had here. So everything was explained yesterday, and for more details, you can look at this paper in which they try to summarize all existing evaporation rate at up to 98. But at the moment, we have only some changes, and we try to move the focus on multi-component sprays, but this is not the scope of this lecture today. So the question was how we will determine the properties of the temperature of the mixture fraction we need for this mass, the evaporation rate, and the quantity which appear in this heat equation. And we have introduced this, we have said that we have to take the reference state, and this reference state is obtained, for example, we see here the evolution, for example, for the temperature. So we have the temperature at the interface, and we have, this is this temperature, and we have also the mass fraction at the interface, how we can determine the reference condition, the reference quantities within this layer. And to determine this temperature, the reference, and the mass fraction, so we have two type of formulations. It is called the 1/3 rule or 1/2 rule, and the half rule. And this is provided as it is here. So we have the value at the infinity, yeah, plus this ratio, and we have the quantity at the interface, yeah, and minus the value in the infinity. And by doing this for the temperature, for example, we obtain this rule, and for the mass fraction, we obtain this rule, and that is why we have the temperature of the reference here and the mass fraction, the reference. And the behavior is the mass fraction will decrease and the temperature will increase. We see that we have naturally, I put all values or properties. We have the thickness of the based on the molecular layer and here on the temporal layer, and it is the radius of the total from using adding this layer here plus the radius of the droplets. We say because the dimension of the droplets is changing with the time, then we will have also different drag coefficient and naturally or different Nusselt's number, which account for the turbulence effect. And we have said this will also depend on the thickness of the film we consider of this film here. If we say that this film is as a constant thickness or as a variable thickness, we have different rules, and this has been obtained experimentally by different people, and we have here some correlations for the effective Nusselt's number. That is what we have derived for the constant film thickness. And if the film thickness is not constant, and we see there is a dependency on these thermal Spalding transverse number. And we have different expressions and also the rule we can use if we account for these kind of correlations. It is the same for the Sherwood number. And yesterday we came here, it is also the same for the drag force. And for the drag force, we have the drag force for non-evaporating, so where the diameter is constant. And here, if we have the evaporation process, and the CD will depend on this value here, and naturally depend also on the Spalding thermal transfer coefficient and transfer number. Let me give you some example. If we use the equilibrium model and non-equilibrium model for this single droplet experiment, it is for water. The gas phase has this temperature of the liquid is, so we need the time to heat. And here the time is very, very short. And we see that we obtain directly what we said yesterday, the D square rule. That is exactly what we have obtained yesterday. And the temperature, so we have, the temperature will rise and stay constant, both for both equilibrium and non-equilibrium model. If we have in this case that the Reynolds number is 0, so quiet, and the starting, the diameter is 1.1 we have here. So if we consider, for example, the it is for different temperatures, we obtain that the evaporation follow this rule here after this heating period, and we have a good agreement between the simulation result and experiment. Here we have usually the equilibrium model, and this startup part, we could not obtain it correctly because we have neglected this change of the density of the liquid with time as we did here. If we have this, we didn't account for this term, we say that this density is constant. That is why we don't have this startup where the droplets start to grow and then to decrease its size. It was too quick because I had to take this also. And here we have large droplets. It is a decline. And we see that for large droplets, the equilibrium model is more accurate, and the non-equilibrium model, so here every process is like equilibrium process, and that is why the non-equilibrium model does not capture correctly this effect, and the temperature so is provided as it is here. So we have a quick augmentation of the temperature with the non-equilibrium model, and it remain constant after a short time, here 1 second, for example. And this was the remark I would like to put, that this effect is the quantity we didn't consider, the variation of the density of the liquid with the temperature. But for all the temperature we have considered, so there is a very good agreement with this square rule. Let's now go to spray. For that, we need source terms, which include the phase change contribution. Yesterday, we have seen how we obtain this term. So we will have this term plus additional contribution due to evaporation of the particle. And this is this quantity. And here we have to change a little bit. So you have to correct this. Here we don't have m dot, we have m as we introduced it yesterday. You don't have here the evaporation rate, but here we have the evaporation rate, and the moment it will update this quantity. So let me show you the rounds slide, in which we will try to quantify now the mixture formation. So we have shown the phase change, and we have now here to show the mixture formation, how we can quantify it. We can quantify it by using not this SMD, it is not the Sauter mean diameter, but it is the spatial mixing deficiency parameter. And we have to provide a grade of heterogeneity of the mixture. I could not find a better acronym for that. That is why we call it also as SMD. And this SMD, let me introduce it first. It is defined here. I will come back. So this SMD is if we have spray, so we consider a plane, and we consider the error mass of the quantity here, and we divide by the average on the plane of this quantity. And this provides us the SMD. But at the moment, we didn't consider this. We only try to see if we are able to account for, to capture the correct behavior of the spray. This is the spray that is coming from here, and it's spread within the combustion chamber, and that is for non-reacting case. And we see, if we compare with the experiment, the blue dots are experimental data. And we could here observe that our results agree well with the experimental data. But here we can see something which is very interesting. So because experiment is limited, restricted to capture the behavior of the spray because of the access to the chamber. So we have only a very limited access to the domain. So we have only this view here, but by means of numerical simulation, we can obtain the whole view of our combustion chamber. And here we see that we have the radius, so we can have directly the all expression, all behavior of the overall behavior of the spray within this chamber, which is not the case with experiment. And that is why numerical simulations are important, because they allow to provide a very good view of the process within the computational domain, within the combustion system, within the energy system we are looking for. And we did this first. It was for an N-heptane, and then we did this for a very practical combustor. This is a Rolls-Royce combustor 710, and it is it is a 1/8 of the combustion chamber, and we see here our computational domain, and that it is how we did it with these. We have some holes here in which we get some the cooling here within the chamber. And the question was at the outside here, Rolls-Royce would like to get the profile of the radial temperature distribution at the outside, because this is very important to see which impact the combustion chamber can have on their turbine, on the turbine blades. And this was experimentally investigated by Rolls-Royce, and the result of the experimental temperature profile is this one here. That is the minimum. They provide two values, a minimum and a maximum, but they could not see exactly, and that is the maximum, and the mean value was this one. And they would like to get a simulation which could validate this experimental data. And for that, it was our first project with Rolls-Royce. I didn't put the year here. We tried to, it was at the time we have developed our modulation model. I have shown you yesterday. It is the black lines here. And we compare the performance using the prediction performance of the code using this model and using the standard one. And we see here that using our model, so we could be able really to predict the correct behavior of this temperature distribution if we compare to the standard one. And that is the reason Rolls-Royce decides to cooperate with us from the past up to now, and we have a good cooperation with Rolls-Royce. So we did the full two-way coupling, as we have discussed here. So the numerical droplets, the number was 30,000, and the mean diameter was this, the spray angle was this, and we use at the moment the RAS model, and the inflow condition of the turbulence intensity was 10%, and it is the air-fuel ratio, and the temperature at the injection was this here, and the pressure was this. And the model, as I have seen yesterday, so you have introduce some combustion model. At the moment, we have used the steady flamelet combustion model. We also try to simulate this confined circular chamber I have introduced also yesterday. Instead of solid particle here, we have sprayed the isopropanol droplets, and we have investigated this. It is the so-called Sommerfeld and Q configuration, but this was carried out by using LES. And here we compare also the outcome using the non-equilibrium model and the equilibrium model. And we will see here the difference. We have, please remember that here we have large droplets, and here we have small droplets in which we have almost the same behavior. And here we have this spray, and we will see the prediction capacity or capability of these two models. If we look at this position here, so we have this configuration. I have explained it yesterday. So we see that the non-equilibrium model for this case predicts very well the droplet size distribution comparing to equilibrium model. The reason is that this spray give rise to very, very small particles, very, very small droplets, so that there is a very, we have non-equilibrium processes within the droplets, so that the Clausius-Clapeyron equation could not be valid. And for that, the Langmuir-Knussed approximation was the correct one. And that is why we use first the non-equilibrium model for energy, for nozzle, which produce very, very small particles instead of equilibrium model. So this part introduced the effect of turbulence droplet interaction and the effect of spheral intensity. Here we will now try to quantify correctly this mixture formation. And the first case was to account for non-reacting spray. This configuration corresponds to an experimentally investigated configuration in Karlsruhe. We have our nozzle, we have discussed the last, I think it was yesterday, as we have introduced different from spray. So we have our sphere here, we have, it is air assisted. We have here the film, which is built on this lip here, and then through the sharing due to this hair, we got the spray, the atomization at this position. So the gas phase conditions are provided here. There is the swirl number, which is provided. And we have also the droplets properties. So the initial condition, velocity, we have the axial velocity, and we have also transversal velocity, and here we have the radial velocity, and we have the longitudinal velocity, and the particle mean diameter is this one. The temperature is almost this temperature for the gas phase, and it is for the droplets. So we have evaporation, and it is not reacting at the moment. So what we obtain, we have these different properties, and at the end, let me compare. We use here runs, and we have the experiment. This is the streamlines we obtain from experiment, And we use the explicit algebraic Reynolds stress model based on Gasky Gasky-Sarkar model. And this model could help us to reproduce almost exactly the experimental data. As you see, the corner recirculation zone and the central recirculation zone. And here it is first without particle. And so now we show the single phase means without particle and here with particle for the streamlines first and the temperature field of the gas phase in the combustor. So we see that there is not a very large difference. So the single phase is this recirculation goes up to here, but if you have carrier phase, the streamlines are a little bit different. And we see it very clearly in the temperature distribution for the carrier, for the single phase. We have high temperature up to this position. And if we have particles, so there is a change in the behavior of their temperature distribution. And the question was how we can quantify these things with respect to the mixture formation. That is why we try first also to quantify their profiles. First, we try to compare the prediction using different turbulence models. And here, the first one was the K epsilon and the explicit algebraic Reynolds stress. And we had also the second order model, lambda Rhys-Rody model. And we see that we got almost the same distribution at the same profile of the velocity at the beginning. And then we got a deviation. So K epsilon model could not predict correctly. And the Rhys-Rody also not correctly, but the explicit algebraic Reynolds stress will provide the correct behavior. And we got only experiment of these two sections, and we perform the we got the results for the other section, and we produce only for the explicit algebraic Reynolds stress model at this position. We assume that they are correct. After that, we introduce the dispersion. I will explain you in a few minutes. And we could also see the spray penetration and also the droplet concentration zone in chamber by using these two models, non-equilibrium model and equilibrium model. So and here we see the effect of this equilibrium and non-equilibrium model. We see that the penetration of the spray is correctly predicted if we use non-equilibrium model. And if we use equilibrium model, so the penetration is a little bit over-predicted. That is why I say again that the non-equilibrium model is very good for such kind of nozzles, which we found in different application of energy system for, let's say, in combustion systems. So now I come to this influence of turbulence intensity on the evaporation rate along the spray core. So we have our chamber, and we got the result for the evaporation rate. Here we use only the non-equilibrium model because we assume that it is the correct one. So we have first the evaporation rate for 50% turbulence intensity, and then we change the intensity of this, and we see that we have the effect we have an influence of the turbulence intensity on evaporation rate. The question was, in this part, we see two parts clearly. So in this part here, the turbulence, if the turbulence intensity is enormous, then also the evaporation rate is also higher. And in this part here, we see that we have a little bit another behavior. So we follow this one, the black one here. We see that it's changed the behavior here. And here we can say if the turbulence intensity is high, the evaporation rate is decreasing very far from the nozzle outlet. By looking at this with care, we have the idea to introduce the so-called Dam-Kohler number for the evaporation. There exists a Dam-Kohler number for the turbulence and for the combustion. And here we define this Dam-Kohler number for the evaporation. It is quantity which helps us also to quantify the effect of turbulence intensity on evaporation rate, like the Dam-Kohler number in the combustion allowed to quantify also the effect of combustion, of turbulence on combustion. And we got this point here, the point here correspond to Dam-Kohler number equal to 1. And we see if we are in this part here, so this is our Dam-Kohler number, it corresponds to 1. So you see, and if the Dam-Kohler number is smaller, then we are in this region. If it is higher, then we are in this region. So we can say that with the Dam-Kohler number of evaporation, so we got these two regions, then we can characterize the effect of the turbulence intensity on evaporation rate. The other one, the last point was to quantify the mixing process. That is the conjugate effect of turbulence and swell intensity on mixing process. So we start with the variation of the special mixing deficiency along the chamber. That is the quantity I told you before, and we will define it here. What I have introduced here, the average on the plane, we obtain it in this way. It is the number of samples and the RMS, so we obtain these also in this way. And if we see the SMD, not the sort mean diameter, but the special mean mixing deficiency, this means if this quantity is, it is a degree of heterogeneity. If this quantity is small, mean that the mixing is complete, is better than the case when this quantity is higher. We see here, if the swell number is, we have no swell number, this is this plot here. And if the swell number is enormous, so we have by 2 at 0.5, we have this here. And if we have a swell number equal to 1, we have this. And this is a very nice demonstration why we need swell in such kind of system to enhance quickly the homogeneity of the mixture. And if we want to augment the homogeneity, so to diminish the heterogeneity, so we need swell number. And this is also very clear here in this plot. I make everything now very clear. If we have the swell number here, so we have, if we have this 1, it is what we had, but I zoom it a little bit. if we have the swirl number here, so the swirl number is high, then we reach the complete mixing, the very good mixing very quickly. Here at this distance, the mixing is homogeneous, and for the other, we need more more time to get the complete and correct mixture. And if we have reacting spray, the result is almost the same. If the swirl number is high, so we get not at this position, but a little bit later because of the interactions between the chemistry and the turbulence. And if we are at this position 0.5, so we get it at this position very late. And with without swirl number, you see that we get the homogeneity, so very, very, very late, and it will not reach the degree we can get with the swirling. So this is the mixture formation, the degree of how to characterize the mixture formation, how to characterize the effect of turbulence on evaporation, how to characterize, how to quantify also the swirl intensity to get a correct mixture formation. At the distance, we can also want to get, as we have here, we can say we will get the heterogeneity, the homogeneity at this distance. Then we can carry out simulation by changing the swirl number in order to get this at the correct position using this quantity. So I have spoken here about dispersion. Let me now introduce the dispersion models. I have it here. We'd like to introduce now the dispersion. So this is the question we have in many, many papers. If you would like to get a correct behavior also of the turbulence and its effect on different microprocesses. We know that if we based here on the Variant Lagrangian as you are doing now, so we have the particle position, the velocity, the particle motion with different forces. From this, we get this with different forces. And we have our force, the drag coefficient, and here the buoyancy effect. This term could also be neglected, but we put it, it is normally very small, and that is why we consider only two forces. As we have seen it yesterday, we have a lot of forces, and how relevant these forces are depend on this ratio here. And if this ratio is very small, then all the forces will be neglected and we remain only with these two forces, gravitation force and the drag force. The question is now how this particle here, which are crossing this flow, the flowing gas, will be affected by the fluid turbulence. For that, we can introduce this quantity. We can consider the quantity we have introduced, the Stokes number. It is this ratio, relaxation time divided by integral length time. The integral time for the turbulence. If this quantity we have said yesterday, I think, so if this quantity is very small, then we say that the particle follow the fluid. If it is large, we say that the particle will not follow the flow. And if it follow the flow, then it will be impacted by the fluid turbulence of the it will be impacted by the particle will be impacted by the fluid turbulence, so that it will follow the turbulence of the fluid phase. And the question is now here, that is this fluid flow velocity, how we can now get this quantity correctly. Normally, if we use rons, so what we have, I think I provided here, yeah. If we have this quantity there, if you use LES, we have the filtered part and subgrid scale part. And we get from LES only this quantity. We have to add this other quantity. And I told you yesterday for one example we had, we need the expression for this, and we can use only the one equation model, for example, and we have the subgrid scale turbulent kinetic energy here. If we don't have the one equation model as we did in our example yesterday, we can also use the Lilly. If you have runs, we will have the mean quantity here, and here we will have the fluctuation. And this fluctuation can be also be obtained exactly by in the same way. And we have the fluctuation, and we have the variance here, and we have the fluctuation. It can be obtained from the kinetic energy, and it is two-thirds of the kinetic energy. So this means that we need this quantity, and this quantity we have either the mean or the filtered, and we miss the fluctuation part or the subgrid scale part. Practically, what people do, if they do not consider the turbulence dispersion, they have to resolve a large part of the turbulence. This means they say we resolve more than 80% of the turbulent kinetic energy. So we can say that we include in this filtered part the main fluctuations, so that we can perhaps neglect this subgrid scale contribution. But the correct criteria to do it is to calculate these Stokes, this number here. And if we have this number with the different area I have told you, then you are on the correct side. So that is everything I have told, and we will try all the example I have told you. So we use this dispersion model, the AD lifetime model, and the model we use for runs also can be also extended for LES. And here I show you the effect of turbulence, of dispersion. For example, we follow one particle here, and we see if we inject one particle, it will impinge the wall and change the trajectory. It depends on the droplets size, and for very high, for particles which are very large. So we see that there is not a big effect of the fluid flow, and this is also the case for that. But for small particles, we see that there is a very big effect of the fluid flow on this particle. And we see here, if we zoom this part, we see that the particles are affected by the fluid flow, and this is what we call the dispersion effect. The AD lifetime model is very simple. We say that there is interaction between the structure of the turbulence and the particle. If one particle is in interaction with the structure, then it is influenced by this particle. And we assume here that we are dealing with small particles so that their Stokes number will be very, the relaxation time will be very small compared to the AD, to the integral length time scale. And in this case, there is interaction if the particle is within, it is an interaction with these eddies, and if this eddies is no more there, so that is why we call it the lifetime. The lifetime, during the lifetime of the structure, we have interaction, and it comes to the next one, and so on, and so on, and so on. This means that the model is very, very simple. We have this fluctuation. It is in interaction with our particle. And if we have the kinetic energy, we can get this fluctuation here. And we put in our expression there, and we get this quantity. So this model is very simple. The fluctuation works as long as the eddy exists. So during the lifetime of the eddies, but it is discontinuous, as we see, between two two events. So there is no interaction with the eddies. And we cannot consider the anisotropy and inhomogeneity of the turbulence in this. Everything is homogeneous, is discontinuous. So the main shortcoming of this continuous fluctuation is not guaranteed. And this can be, as I say before, we extend this to LES and we obtain this kind of expressions. This is usually implemented in commercial safety codes. And to make the game very, very realistic, the question was how we can transport the fluctuation, the fluid fluctuation at the position of particles. Meaning we follow really the particle and we get the interaction with the time of this particle with the fluid phase. And for that, we consider so-called the Lagerfeld model. And this model accounts for anisotropy and for different effects. So the first one, we have the fluid drift term here. It accounts for the change of the fluctuation due to the change of the fluid velocity. We have here the change of the fluid velocity in the gradient of velocity of the fluid flow, and here the change of the Reynolds stress. The second term accounts for the drift between the particles, here the relative velocity, and the mean flow velocity, to take into account the homogeneity of the flow phase. And the third one, consider the memory effect. We relate the new fluctuations, this one, of the fluid phase to the previous one by this Lagrangian timescale. And the fourth, the last term, explains the diffusion process by including randomness through the Wiener process here. It is a stochastic part. And this Lagrangian time can be calculated using this. We put only the expression, but this all can be correctly derived in the papers. And has been derived in the papers. And for this, we need the two coefficients. We have two parameters. This is the C1, C0, it is 2.1, and B, it is the so-called Snanadi factor, which are used to estimate the difference between the streamwise and the transversal time scale. So this can be implemented. It is sometimes complex, and we can get some reduced formulation of this. And to get the correct behavior, as we say here, we say that at one time, at the time t equal to 0, we have the interaction between the structure and the particle. And after a time delta t, we have this particle is, for example, in this position, and the structure is there. We have to account for the memory effect, and we account for different time, the Lagrangian time, and here the Eulerian time. So if we assume that we have to deal with the homogeneous turbulence, all this term in which we have the gradient part disappear, and we don't have the this complex term, and we have only this memory effect here and the Wiener term, and this is a variance part, and we can get all this quantity very simple. But because it is homogeneous, the Lagrangian time will be the same for all directions. We can also consider so-called the anisotropic random walk model. We consider this term and this term, so we add only the term in which we have this anisotropy. That is why we call it anisotropic model. We consider an additional term in this isotropic random walk model to account for the anisotropy. So for this, I come back to this. It is in Germany, has to be, but I put it, it is the model reduced and proposed by Sommerfeld based on the Langevin model. It is this model here, where we said that these fluctuations are Gaussian distributed, and we can calculate the fluctuation at time step n+1 based on the fluctuation on the time step, the previous time step, and we include the Wiener term. So for that, we have these correlations. The correlation we obtain from these two, this is this here, and it is a Lagrangian one, and it is the Eulerian one. And the Lagrangian one and the Eulerian one are obtained from some idea from turbulence, and we obtain that it is exponential to minus delta t divided by Lagrangian time, and the Lagrangian time, as I told you, is exactly this one. It is proportional to the variance here. In this way, this coefficient was calculated or was proposed based on homogeneous isotropic turbulence. For the Eulerian coloration, so I think you know this, I didn't put it here. So for Eulerian coloration, we have these two kind of, we have the first correlation with correspond to the delta R divided by the Eulerian length scale, and this one here, and we put both together, and if we put the both together, we have this correlation, and we put this correlation together, we have this function, and we can put them here, and we got our fluctuation of the particle at, of the fluid phase at the location where we have the particle, so that we have removed this discontinuity, and we can track our correlation in the correct, our particle, and also the influence of the particle, of the fluid flow on the particle in a correct way. We did a first validation of this. This is only for your information. So we did the calculation of the mean deviation, the mean square deviation. And we obtained first without particles, we obtained this behavior. And then we put some particle within with the experiment. If we have the particle which are not felt, and here we have pollen, and we have a glass particle, and we could obtain the correct behavior of this deviation of our velocity fluctuation. So it is the deviation of the velocity with respect to the mean value. And we see that if we consider this dispersion model, so we can obtain correctly the behavior we are we are looking to include in our calculations. Here we did also validation of these models. And this is the experimental setup. It is a wind tunnel and particle image velocimetry. So the particles are introduced here, and we have a shear this here, and here the particle will be dispersed, and it is captured by the camera. And we have tried to get the to follow the particles and to get how they will disperse within this channel by using naturally different dispersion models. So we use this Langevin model, we use the reduced isotrope model, and we use the anisotropic model. And the model was the K-epsilon model, and it was a paper we published in 2015 with Moldy and myself and Vide. So we could see the difference here. What is to see? To see is, I will focus on this first. We have tried to capture correctly the mean value of the velocity of the particle. And we see that we could get it very good with our random walk model. And here with the Langevin model could get the correct prediction, could provide the correct prediction, but it is costly. That is why we have tried to compare with this model here, the anisotropic model, which is now here. And we see that if we try to calculate the mean concentration of particles predicted by these different dispersion models, so we see that we have a large deviation if we consider the random walk model, the isotropic one, but isotropic one follow the prediction of a disposition and disposition of the Langevin model. That is why we use normally in our applications the random walk model. And at this point, there is a large deviation. We could not explain it. So we did also the same in this configuration, this Sommerfeld configuration. And we see also the same behavior that we have an isotropic model is not very good, but the anisotropic model and the Langevin model will provide everywhere the correct behavior. So my message is, it is better to use a dispersion model if the Stokes number allows, if the ratio of the relaxation time divided by the integral time of the fluid flow is very small. The same results follow here. It is only to demonstrate to you that everything is correct, and that is the output, the good result with the Langevin model with respect to mean velocity, mean diameter, and velocity fluctuations. And with respect to LES, so we could transpose the AD lifetime model to LES if we are able to capture the correct subgrid scale models. And also we can use also new models. So here we try to use the motion equation of particle, but we add an additional term, this term here. It was formulated by Jones, and it accounts for the turbulent dispersion. And this turbulent term is out of a Wiener process in which we have the subgrid scale and the time scale and the Wiener process, increment of the Wiener process. And this additional term influences the droplet particle motion during the time, and this time is proportional to the particle relaxation time or the response time. And this is also consistent. We put this quantity here and we add it directly on our transport equation of our particle. Here we have the milled, the filtering part, and we have the fluctuation part. So this means that the part we add here is implemented here to account directly for the dispersion in LES. So that is the first part. We complete what we had yesterday. And I think at this point, you can have some questions, but let me continue directly so that you will put the question directly at the end. Only if you see that you cannot take time to put your question, then you can put the question now. Otherwise, we will continue with the turbulent spray combustion. We will start with the droplet burning. We will introduce this homogeneous combustion, heterogeneous also, and we will see different combustion modes and regime, and we will see some overview of turbulent combustion models. But this part will be very, very short because I have seen that Shoke has introduced this also in the to prepare this chapter. What I would like to say at the beginning is that we deal with turbulent spray, and this is a very complex phenomenon, as we have seen, as it occurs, for example, in such combustion chambers I have explained before. We have to deal with the turbulence mixing it and mass transfer. We have two-phase flow phenomena, means interaction between phases. We have chemical reaction. We can have also radiation in this. This means that it is very complex, but to get a very good prediction or to have a mean to control the process or the system itself, or to be able to design, to add the design or the optimization of this process of the system. So we need really numerical simulation. And because we need numerical simulation, we see that we need different models for describing these processes. And we need also numerical method, actually. And we have seen how to do it. And normally what I do, or what we do in our group, is to design models which account for all these systems together, because they are coupled. And because they are coupled, they have to fulfill the second law of thermodynamics. So they have to include, we include then the entropy, the balance equation of entropy, or the entropy inequality equation, and so that we can get a very good coupling between different models, so that the system will provide us, the solution we will get will be really thermodynamically consistent. So we introduce this modeling. We say then we have here turbulence and mixing model. We have a two-phase flow, primary breakup, secondary breakup, interaction between phases. We have also chemistry. We can define it, reduce, and it comes in interaction with the turbulence. We have a chemistry turbulence interaction model. We have here different models. So you have seen some in which we didn't consider the two-phase flow. So the PDF and a different regime of the chemistry, premix, non-premix, also partially premix. And we can have also heat transfer process, radiation, and each part here interact with the other part so that we have a very complex thing. And this was the part introduced before, and I can say this part has been introduced by Professor Ashoka, and here I consider all these parts together. So what we did up to now, we investigate spray injection, atomization, modulation, turbulence dispersion, and vaporization. Now we have to add combustion and heat transfer if necessary to describe all these 5 sub-processes I have introduced at the beginning. Atomization, phase transition, transport, mixing, and combustion. So we have this picture. It is exactly this one. It is 2D representation. It is our 3D. So we have heat transfer, interact, bring heat to our droplets. These droplets evaporate, and we have some fuel vapors. And if we get a flammable mixture, then we have in interaction with oxidant. So we have a flame, and this flame sheet can develop, and we have some product. So we can say we have the internal region and we have the outer region of our flame, of our system. Remark, so we have seen that only considering the phase change, we obtain this evaporation rate without accounting for the effect of chemistry of combustion. We obtain this in this way, so it is only an alternative. So we get this expression as function of the mass transfer Striding number, but here also we have seen the rule we have if we try to represent the evolution of the temperature and the evolution of the mass fraction. And if we have, for example, the flame, we'll have the burning temperature here, then we will have almost the same profile, but the quantity will be different. And that is why I tried to show you also yesterday how we can relate this evaporation rate with the temperature, because the main output for the combustion is the change in the temperature. And we got this expression also yesterday, in which we got this Spalding heat transfer number in this form. And this is the quantity we need to warm up our droplets. And we had the relationship between this quantity and this one. It was related by this expression. And there we have the ratio of this capacity coefficient in connection with the lowest number. And if the lowest number is equal to 0, there is no problem. So these two quantities are the same. If the lowest number is not equal to 0, we have differential diffusion, and for the evolution of the temperature of the droplets. So we have got these 3 terms, this one, the first one to warm up, and this is the latent heat, and it is the part due to the chemical reaction. This means that in this expression here, we will get additional contribution due to the heat, and this quantity also will be will provide us, will be completed by an additional term which account for the heat of combustion of the fuel. And if we consider that our assumption we had before are now also valid here, we can say that the previous model we had is now extended to include diffusion flame, for example, that surround the droplets. This means that the droplets is at the boiling point. This restriction is now removed. We consider the moment one step overall chemical reaction. So fuel oxidant, we have the product, and we consider the Book-Schumann limit. This means that we consider large Damkohler number, and this means that we deal with infinitely fast chemistry, and this means that we have only the reaction in thin reaction sheet, as we showed here. Okay, the flame sheet. If we have this in a dimension form, the burning rate, so what we had before, will be completed by this term here, the heat of combustion. And this BT, okay, this term, what we had here, the Spalding heat transfer number will be also completed by an additional number, additional quantity. And this is this quantity, and this is the contribution of the chemical reaction on the heat. And this quantity is only the impetus for transfer divided by resistance to transfer. And this relation has been proposed or established by Moshe Matla in 2014. If we have this extension, we can demonstrate it. And normally I put it as an exercise, and people did it because it is not complicated. If we do it, we have to find also the position of the flame. Okay, the flame stand of distance. It can be obtained using this. If we have this quantity, we have everything here, and we have this quantity, and we say if this quantity is larger than 1, imply that this quantity is larger than this, and we obtain this from this relationship. And this quantity we can get, and it is exactly what also we obtain for the evaporation rate. And here we have the same. We have our flame and the outer region. So we have the product. We have the temperature with the plane, and O2 will be produced. So the flame, we have the flame stand-up, a stand-off distance. We can also have the temperature of the flame. The temperature of the flame will be equal to the temperature here plus this quantity here. So I will not like to derive it, but this quantity is only the contribution of what we had here. If you see what we had here, it is the contribution of this part to the temperature, and we can derive it as exercise. It takes, I think, 2 pages to get the results, but here you have only to account for the result, the final result we get. So we have the standoff distance, and we have the flame temperature. We have the flame temperature, and we have the standoff distance also. Good. Let's now move to the turbulent spray combustion. This was the combustion around the flame, because we will need this sometimes, but for a spray it is very complex, and we deal with a lot of, a large number of droplets. For that, we will distinguish two kinds of spray combustion: homogeneous spray combustion and heterogeneous. So by homogeneous, there is no interaction between the spray and the flame. So we can consider this picture here. We have our droplets. They are evaporating. You see that the size of particle is decreasing. And we have the fuel vapor here. And this flame vapor rate is stoichiometric conditioned, and we have the flame. This means that the flame occur very far from the droplets, so that we don't have interaction between the flame and these droplets. And we can see this here if we consider to a counterflow flame. So we have oxidizer, oxidant here, and we have the flame front, and we have the fuel, and here we have the oxidizer and the flame. The particles are all evaporated before the start of the combustion. So if we have interaction between this, what we had before, if we are at this position 1 here, we say that we have heterogeneous spray. At the position 3, we have homogeneous spray. And in this part, which is the point is that if we represent also everything in this counterflow flame, we see that the droplets has not enough time to evaporate completely, and the part of the droplets enters in interaction with the flame, in the case of diffusion flame here, and it should be also diffusion. So we see that we have interaction between the flame and the particle. So in many applications, in many works, in many contributions, people use this kind of combustion. So homogeneous, because it is simple. We can use the models we have developed for single droplets, but with some correction. For example, if we include the mixture fraction, we have to consider the source term of the source term due to the evaporation of the droplets, will change a little bit the composition and also the mixture properties. So with this, we can now categorize different combustion modes. If we have our fuel vapor, okay, and we have our droplets, the droplets can come out, and we have what we did at the beginning. We have single droplet flame. The flame is surrounding the droplets, and we know the position of the flame. We know the temperature of the flame, and this is so-called single droplet. If we have, for example, a number of particles which could not evaporate completely, so that we have some particles, non-evaporating particles within, surrounded by flame, then we have the so-called internal group combustion. And we have also this single droplets combustion, but we have here internal group combustion. And they are separated. If all the flame, if all the droplets are surrounding by flame, then we have the so-called external group combustion. And if we have both combined, so we have non-evaporating core, and we have also some droplets here surrounded by the flame, we have the so-called external sheet combustion. And I put them together here. This is a view in axial plane, and this is a view in radial plane. No, it is a plane, a radial plane, and this is axial plane. So we have a single droplet. We see these droplets surrounded by the flame. We have internal group combustion, so we have evaporating droplets enveloped by flame, and we have also some single droplets, droplets combustion, and we have the so-called internal group combustion. We have this external, everything is evaporating within, but not completely, and we have the flame, which surrounds all these droplets. And here we have the combined parts. So we have non-evaporating cold flame droplets, and here we have evaporating, and the flame is there. And this was proposed by Xu, 1999. And this is an experiment by Mastry from Sydney, in which we can see some droplets here which interact with flame, but it is not really visible. But it was only to give you an idea how these droplets can also traverse flame. Based on these things, on these physics, people try to generate a combustion group map or group combustion number. And this combustion number has been derived, and we could classify these different group combustion using these combustion group quantities. And for that, we use first this distance between droplets, as we had learned before. This quantity is proportional to this ratio of the diameter of the droplet and length scale. And here we have the number total of droplets. For that, we decide to get their group combustion number, and we could classify this here. Let me show where it is. Yeah, it is here. And we have the S, it is this quantity here, and we have the number and the combustion group combustion number. It is the ratio between this number here, 2/3 divided by S. The S is this term which is which include the distance between two droplets. And using this, one could obtain this diagram in which we have the external group combustion, internal group combustion, and single droplets, and the external sheet combustion based on this quantity here, which is there. And that is what we try also to put here. So we have the single droplets, we have internal group, and we have external group and the external sheet. And this is only the spray which is coming out. And this is the value of this combustion, the group combustion number, which is defined as the ratio of this here, 2/3 divided by this quantity, which include this ratio we had at the beginning. So I put everything here together for a summary, to summarize everything. And now let me put an example, not for spray, but for oxycoal. It is exactly almost the same. Here we have a solid particle, but solid particle which need also to devolatilize. It is a kind of evaporation. And then we have the, so due to heating, So we have first the devolatilization, and we have the volatile, which will start to combust, to be burned, and then this combustion can influence also the combustion of the COX, and we have also sometimes radiation. Let's come back to this configuration. It is a paper we did in the past, but this configuration has been investigated experimentally by the group of in Karlsruhe by Kner, and this is this nozzle here, and the coal are injected here, and we have this different nozzle. The particles are injected here. We have two parallel injectors, and we have also another one here. And I will show you in the next slide. And this is what we generate as grid. And the benefit of oxy-fuel combustion is first, the lack of N2 is allowed to increase the flame temperature. We have a high water and CO2 concentration in the flue gas, which can be recirculated to improve the radiative transfer. We save fuel, and we reduce also CO2 emission, and this can be used in different industries like aluminum, steel, glass, and cement industries. I have introduced these also before, I think, at the beginning of this chapter, of this lecture. So for that, we need models to describe all these processes. We need the volatilization model, combustion for volatile, combustion from COX, and then experimental data to compare our result with experiment. So first, we transport the particle. We transport the particle using the Lagrangian framework, and we have different processes. This, the devolatilization and combustion. This means that we need these two additional transport equations. We need the transport equation for the particle, for the temperature of the particle, and all for mass. And here we will do it here. We have to transport charge. And using this, we use exactly the expression we have derived here. We have this part here with the part which include the reaction part, and this is which consider the heating. So we use also for the Nusselt's number correlation. It is based on the Rance-Marshall correlation, and the particle heat capacity and particle density, they are set to this value. Devolatilization, so we use the single first order reaction. There is a lot of, but we use this one here, and for that it follow Arrhenius assumption. So the variation of the mass fraction of these particles coming out from the coal is only given by this expression. I go not in details on the composition of this char, but it is a Rhenish lignite. So the char conversion is calculated by this by Baum and strict model. So we have this, and we include these two kinds of diffusion coefficient, and these diffusion coefficients are given here. This is first for diffusion, and this one is for the reaction rate. And this quantity here provide the reactive surface, which is make available, and we have this change is due to the porosity, so that this quantity is expressed in this form. There are a lot of correlations if we are dealing with coal, and we carried out the nozzle is the gas assisted nozzle, so that it is a gas assisted coal combustion. Now, using all these expressions for LAS model, so we use, I think it was the whale model. I didn't remember again, but the details can be found in this paper here. So we compare first the experimental data with our calculations, and we see exactly what I said you. With the experiment, we have only access in this small range of radius, but with the numerical simulation, we can get all the information. And it seemed to be symmetric at the beginning, but not really, because this configuration is very complex. This is what we have as a computational domain, and this is a photo of what we had as nozzle with this different entrance. I have shown you before. Would be better to put it here to see exactly, but I have shown you before this different entrance here. We have S1, the particle S1, S2, and this is for the here. Now we have different results here with the particle, without the particle, and here only the flow field. And we see that we could be able to track the particle and to get the temperature evolution, and to be able, I think, to get this result as we obtain here. They could not measure the particle velocity, but here we are only the velocity of the fluid flow. And we compare them, and it was very convincing that everything is right. So this is also a very good example of the group combustion we had. And here I give a very clear definition of this group combustion number. It is given here, it is proportional to the number here, to this number, and this is our S, what we introduced. And this S is given here, and as a final expression, we have this. It is followed in terms of non-dimensional distance S, and also the droplets number in our cluster. It is, can put it in non-dimensional interdrop spaces regime diagram, and we have this in this form. We didn't carry out different validation of this model, but I think this will be done in the future. So this is the first part, and we will now focus on the homogeneous combustion for droplets, in which we say that the droplets do not interact with the flame. Okay, in this case, we restrict ourselves to the case in which all droplets are supposed to have evaporated before combustion. And the question will be focused on the fuel-air mixture preparation, in which we say that the mixture fraction variance is modified when spray evaporation is present. This means we will get an additional term in there and in the equation of the mixture fraction. And this will also influence the combustion, and we will neglect extra term in the equation of the progress variable. So these are the setup. Let me see, yes. We have the Eulerian-Lagrangian method. The Eulerian description is given by the by this set of by this generic equation. We have the in different component coordinate x, y, and z, the time variation, and we have the diffusion term, and on the right side we have all source terms. So the source term due to the non-convective flux. And here we have the source term due to the presence of particle. Here we have the source term due to evaporation. We did we gave some example with respect to these three terms. Now we are adding this last term due to the combustion. I show you here something with a coal. It is very complex, and we will see also that it is very complex. For modeling the spray, for modeling the combustion, so we will consider the flamelet-generated manifold. I think you got it yesterday, introduced by Professor Ashoka. And for that, we have two transport equations. We have the progress variable equation. We have the mixture fraction equation. And we can also have the variance equation due to what we would like to provide as model for the turbulent chemistry interaction. In this case here, we consider a presumed PDF in which we need the variance of the mixture fraction. And here we see that the mixture fraction is no more a conservative quantity. So normally for single phase, it is a conservative quantity without the source term here. But now it is no more a conservative quantity, and the source term introduced the effect of the evaporation, which changed the composition and the mixture of the gas phase, so that we have a source term, and this source term is important and make the difference between the single phase combustion and two-phase combustion in this point. And we assume that we don't have here a source term in the progress variable, because here normally we can use also product so that there is no source term. And if we include the presumed PDF, then we have an additional source term here, and the source term has been provided by Professor Gutheil as dependency of the independency with the evaporation rate. If this evaporation is 0, then we don't have evaporation. This term is 0, and this term will be also 0. Good. And having this, I think we got everything yesterday, and I think we can continue in the afternoon. I give you some time to put questions. If not, let me first, so I have 4 minutes. Let me continue. I have 4 minutes. So why do we include the flame-generated manifold model to reduce the chemistry? And I will not like to repeat everything which was said yesterday. We reduce the dimension of the chemistry and not using the detailed chemistry. And for example, here, only to point out the fact, if we have CO and hydrogen jet, we have 11 species and 21 reaction steps. And we use here for IBM computers with so large number of grid point, we need so much CPUs, and on Craze we use this number of CPUs where we have parallelization. So then we can say the full chemistry is required, but very time consuming. And this is why we try to reduce the chemistry. And one way to do it is the 1D detailed chemistry simulation. And here I try to show how we do it. So we have this chemistry CO2, we have methane, and we have oxygen, and the mix. We have here the reaction, the temperature is enhancing, and we have production of CO2 and also of water. And we try now to reduce it. To do it, we take the temperature as function of, we define a progress variable is to the product, so CO2. And for that, we have CO2, and we can also now produce or tabulate all values of the temperature as function of CO2, and also as function of all species we would like to get, so that we can put everything in the table, in 2D table, where we have the progress variable and we have the mixture fraction. And this table provides us all these quantities, as we see from here. And this is obtained by this storage, and also obtained to get this with transport equation, and this is called the progress variable. And this progress variable is then followed. And here only an idea of this map. We have the mixture fraction, and we have the progress variable, and we can store all chemical quantities we want to get here, for example, the temperature, and we can get all the quantity. We can also, all the quantity, for example, density, the temperature, source terms, viscosity, everything. And if we have this, then we know that there is a interaction between chemistry and combustion. It was, I think, introduced yesterday by Professor Ashoka, and we see that we need in our transport equation the filtered quantities. As you see here, we need these filtered quantities, but normally this quantity is a function of the mixture fraction and the progress variable, and this quantity is not equal to this one, because we have a very big interdependency of the quantity, and it is non-linear, so that we can only get this filtered quantity by calculating the PDF. So it is a statistic dependency. And we have this quantity multiplied with PDF, and the PDF depend naturally of the mixture fraction and this progress variable. It is already normalized by this value in equilibrium. This is why we integrate between 0 and 1. And normally it is not easy to get this quantity. We have two ways. We can solve the transported equation of this of the PDF, or we can assume a form for this PDF. And here we can use the so-called statistical independency. And if we say that they are statistically independent, then we have the progress, the PDF the mixture fraction, multiply the PDF for the progress variable. And for the mixture fraction, normally we assume a beta PDF, and here we can also assume a beta PDF. We say that it is only the delta PDF, and then we have these. So we have then to solve the mixture fraction equation, the variance, and the progress variable equation, so that we can get in storage in this tabulated subgrid scale, this for the chemical parameters, this dependency of the mixture fraction, of the variance, of the progress variable. So we have what we obtain from the chemistry. We make this filtering, and we have our tabular lookup table, and this will be called at each iteration in which we are solving our areas. This is how we consider the chemistry turbulence interaction. In the case we have this pressure PDF, and we introduce the transport equation for the gravity. So in the afternoon, so we will continue with some example, and also we will continue with other aspects of this turbulent modeling, and then we will extend it to other kind of coupling between the fluid flow and the disperse phase. So that brings me to the end. You have 10 minutes, I think, or 11 minutes to put some questions. Are there some questions? So you can directly speak. All right. So I see you have no question. If it is the case, we meet in the afternoon. At 2:30. Okay? So I stop this, and I hope that we meet in the afternoon. Do you have some questions?
I don't think that there seems to be any questions. So.
Okay, then we meet in the afternoon, okay?
Yeah. So that way.
Okay, nice. Thank you.
Thank you, Professor.
Okay, bye.
Bye.